So, let's go. 4 astronauts launched to the moon yesterday. Right now, as you're watching this, they're out there. And the thing they're flying toward is stranger, more dangerous, and more poorly understood than most people realize. Here are 10 mysteries about the moon that nobody has solved, including the ones that could actually kill the people currently heading there. Number 1, the crew is already in trouble. They haven't even reached the moon yet. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen launched on April 1st, 2026. Their flyby is Monday, and right now, in transit, they're being cooked by 3 different kinds of radiation simultaneously. The first kind comes from the Van Allen belts, 2 donut-shaped rings of trapped particles that surround Earth. Every mission to the moon has to punch through them on the way out and again on the way back. The Apollo crews did it fast. The Artemis 2 crew is actually spending slightly longer in the belts because of their orbital path, and in 10 days, they'll burn through 5% of their entire career radiation limit. A month on the space station does the same thing. They're doing it in 10 days. The second kind is solar. The sun throws out storms, sudden eruptions that can spike radiation to potentially lethal levels within hours. There's an alarm inside their capsule for this. If it goes off, the crew physically grabs storage bags full of equipment and stacks them around themselves as shielding. They turn their spacecraft into a fort made of food pouches and spare parts and wait. The third kind is the worst. Galactic cosmic rays, particles fired from dying stars across the galaxy, moving at nearly the speed of light. You can't really shield against them. In fact, adding more material between you and them can make it worse, because the rays hit the shielding and splinter into secondary particles. It's like trying to stop a bullet by standing behind a wall that turns bullets into shrapnel. The Apollo astronauts reported seeing flashes of light with their eyes closed, not hallucinations. Cosmic rays passing directly through their retinas and firing the neurons by force. And here's the part nobody talks about much. There's some evidence that Apollo deep space crews had significantly higher rates of cardiovascular disease later in life compared to astronauts who never left low Earth orbit. The sample size is small. The debate is ongoing. But radiation sits at the top of NASA's list of problems for deep space exploration, and right now, as of this exact moment, there is no solution. There's just management. The crew is already in it. Number 2, the moon keeps flashing, and nobody knows why. People have been watching the moon do something weird for over 1,000 years. Brief flashes of light, colored glows, patches that brighten and then go dark. The whole surface shimmering for minutes at a time, then nothing. These are called transient lunar phenomena. And the catalog of reported sightings goes back to the 6th century. About 3,000 reports across recorded history. Some from professional astronomers, some from people who had no idea what they were looking at, but wrote it down anyway. The European Space Agency spent years pointing dedicated telescopes at the moon to count them systematically. Their estimate, up to 8 flashes per hour across the entire surface. The moon is getting hit constantly. Most of those flashes are meteorite impacts, rocks slamming into the surface at tens of thousands of miles per hour, releasing energy in a burst of light visible from Earth. Those last milliseconds, and they're basically understood, but some of them last minutes, and some of them last hours. And those ones don't have an explanation. The leading theory for the medium-length ones is that the moon is venting gas, radon seeping up through cracks in the crust, catching sunlight as it disperses. There's evidence for this. It's plausible. It's not confirmed. The long ones are genuinely open. In 1787, the astronomer William Herschel reported watching a bright glow on the moon's dark side for an entire night, not a flash. A sustained glow on the part of the moon that wasn't even facing the sun. About 1/3 of all reliable sightings cluster around a single region called the Aristarchus Plateau. Something about that spot makes it flash more than anywhere else on the moon. Nobody knows what. On July 15, 1969, the day before the Apollo 11 landing, Neil Armstrong looked out the window from lunar orbit and reported an area that had what he described as a slight amount of fluorescence. He thought he was looking at Aristarchus. This Monday, the Artemis 2 crew has a dedicated window during their flyby to watch specifically for these flashes. The plan is to observe during the solar eclipse phase when the moon's dark side will be facing them. 4 humans floating 5,000 miles above the surface, watching for lights that have been unexplained for 1,000 years. They might see one. They might not. Either way, they won't be able to tell you why. Number 3, the dust will outlast the mission. You've heard that moon dust is bad. You probably don't know how bad. The moon has been getting hit by rocks for 4.5 billion years, and every impact grinds the surface into finer and finer particles. On Earth, wind and water round those particles off over time, smooth the edges, pack them down. The moon has neither. So what you get is a layer of material covering the entire surface that, under a microscope, looks like broken glass. Jagged, angular, sharp at every edge. Particles so small they're invisible, less than a 20th the width of a human hair. And they're charged. The sun's ultraviolet light hits the sunlit surface and strips electrons, leaving the dust with a positive charge. The solar wind bombards the dark side and leaves a negative charge. At the boundary between light and dark, the voltage difference is around 300 volts. The dust levitates. It floats, on its own, about a meter off the surface. No wind, just electricity. When it touches anything, it sticks. Not like regular dust sticks, like it was designed to stick. In a vacuum, the particles lose the tiny cushion of air molecules that normally prevent surfaces from bonding at the atomic level. The dust fuses electrostatically to whatever it contacts. Spacesuits, visors, equipment seals, instrument lenses. You cannot brush it off. The more you try, the more you grind it in. Harrison Schmitt was a geologist on Apollo 17. After his first moonwalk, dust got tracked back into the lunar module. He started sneezing, his eyes went red, his throat tightened. He described it as lunar hay fever. And the dust smelled. Astronauts consistently reported that moon dust, when it hit the oxygen in the cabin, smelled like spent fireworks, like the air after a gun goes off. Apollo crews were on the surface for 68 hours at a stretch. Artemis plans for days, weeks. Nobody has real data on what weeks of low-level dust exposure does to human lungs, because nobody has done it. The dust is almost certainly toxic over time, but we don't know the curve. We don't know at what point it becomes dangerous. We just know the Apollo crews described it getting worse with every single EVA. 2 recent robotic landers sent to the South Pole, both tipped over on landing. Different companies, different designs. The terrain and the dust keep winning. Number 4. The moon is shrinking, and it's not done. The moon's interior is cooling. Has been for billions of years. And as it cools, it contracts. Slowly, relentlessly, like a grape turning into a raisin. Except the moon's outer shell is rigid. It doesn't shrink smoothly, it cracks. The crust compresses until it can't hold anymore, and then one section buckles upward over the adjacent section along a fault. This creates cliffs. Cliff-like ridges that scar the surface in long, curving lines called lobate scarps. Scientists have now cataloged 2,634 of them, including over 1,000 that were identified less than 4 months ago from new imaging data. They're everywhere. The average age of these ridges is around 124 million years. Some are younger, some may still be forming right now. And when the moon snaps, it shakes. Moonquakes from these faults are shallow, and shallow moonquakes on the moon do something that earthquakes on Earth don't do. They don't stop. Earth's interior is full of water-saturated rock and soft sediments that absorb seismic energy quickly. The moon is bone dry, cold, rigid. There's nothing to dampen the vibration. When Apollo 12's crew intentionally crashed the upper stage of their Saturn V rocket into the surface, the moon rang like a bell for 55 minutes. A single impact, 55 minutes of shaking. Here's the part that matters for the people currently flying toward it. The strongest shallow moonquake ever recorded by the Apollo seismometers had its epicenter in the South Polar region. The exact location is uncertain. The network was only 4 stations clustered around the equator, like trying to locate an earthquake in Alaska using sensors in Florida. But the cloud of possible epicenters overlaps directly with the landing zones NASA has designated for the next crewed missions. One of those candidate landing sites has a young thrust fault scarp identified inside its boundaries. There hasn't been a seismometer on the moon since 1977, Everything NASA knows about South Pole moonquake risk is based on 8 years of data from equipment that's been off for nearly 50 years. Number 5. The ice that might not be there. The entire reason Artemis is going to the South Pole, the scientific justification, the resource argument, the long-term base rationale, is water ice. The moon's poles have craters so deep that sunlight has never touched their floors. Not in billions of years. The temperature inside those craters drops to negative 250 degrees Celsius, colder than Pluto's surface. Anything that drifted in and froze stayed frozen. Ancient comets, asteroid impacts, solar wind hydrogen reacting with oxygen in the soil. Over billions of years, ice should have accumulated in those permanent shadows. And there is ice there. That's confirmed. In 2009, NASA deliberately crashed a rocket stage into a crater near the South Pole and watched what came up. The debris plume contained water. About 6% by weight, real ice in the ground at the moon's South Pole. The problem is the estimate of how much. Early calculations suggested there could be hundreds of millions of metric tons at the North Pole alone. The number that gets cited most often implies enough water to fuel human spaceflight for generations. But in 2023, a study found that the permanently shadowed regions are at most 3.4 billion years old, younger than the craters that contain them. The craters are 4 billion years old. The shadows only formed later, after the moon's axis shifted slightly. And most of the water delivery, comets, asteroid impacts, peaked before the cold traps existed to catch it. The estimates have to come down. By how much, nobody is sure. And there's a more fundamental problem. Nobody has actually touched the ice. We know it's there from what a debris plume looked like from orbit, from radar returns, from neutron spectrometers measuring hydrogen concentrations. What nobody knows is whether it's a sheet of pure ice just under the surface, or tiny chunks mixed into the soil, or molecules chemically bonded to mineral grains. Those are 3 completely different things when it comes to mining. In 2025, a drill specifically designed to answer this question was aboard a lander that tipped over on the lunar surface before the drill could deploy. Jacob Bleacher, NASA's chief exploration scientist, described the situation this way. We know the volatiles are there, but we don't know if it's icy dirt or dirty ice. The mission that's currently flying is partly going there to look. From 5,000 miles up. Now, here's where the video shifts. Everything so far has been about threats to the mission. Radiation, dust, unstable ground, uncertain resources. The things that could kill the crew or sink the program. But the next 4 mysteries are different. They're not just about danger. They're about how much of what we thought we already knew about the moon turns out to be wrong. And that's somehow stranger. Number 6. The moon has a comet tail. The moon has an atmosphere. Barely. It's so thin that the molecules in it almost never collide with each other. They just travel in individual arcs like tiny ballistic trajectories between the surface and space. Not really an atmosphere. More like a haze of individual atoms that the moon keeps losing and replacing. Among those atoms, sodium, constantly being knocked off the surface by micrometeorites, by solar ultraviolet radiation, by charged particles from the sun. Sodium atoms escape the moon's weak gravity and drift into space, and when they do, solar radiation pressure pushes them, accelerates them, blows them in the direction directly away from the sun. The moon has a comet tail. It's invisible to the naked eye. It stretches for hundreds of thousands of kilometers behind the moon, pointing away from the sun like a flag in a wind you can't feel. And once a month, during the new moon, the geometry lines up so that Earth passes directly through it. For a few days, every lunar cycle, you're inside the moon's tail. The sodium atoms stream past. You can't see them, can't feel them, can't taste them. But they're there. This was discovered by accident in 1998. Astronomers trying to photograph a meteor shower picked up unexpected sodium emissions in the sky and spent weeks ruling out every other possible explanation before concluding it's the moon. The moon has been trailing this thing for billions of years, and nobody noticed until someone pointed the wrong telescope in the right direction. The mechanism still isn't fully understood. After 30 years of study and multiple dedicated observation programs, scientists haven't been able to definitively determine what's knocking the sodium off the surface. The best evidence points toward meteorite impacts, but it hasn't been proven. The moon is shedding itself continuously into space, and the details of how are still open. Number 7. The moon has two completely different faces, and we only just got samples from the wrong one. Look at the moon. Really look at it. The dark splotches you can see with your naked eye. Those are ancient lava plains, seas that were never water, created by billions of years of volcanic activity. They cover about 31% of the side facing Earth. Now flip the moon over. The far side is almost entirely absent of those plains. Cratered, mountainous, ancient looking in a way the near side isn't. Less than 1% covered by the same volcanic material. Same moon. Two completely different geological histories. The near side erupted for billions of years. The far side barely participated. The near side is also loaded with radioactive elements, uranium, thorium, potassium, concentrated in a region around the biggest volcanic plain on the moon. These elements generate heat as they decay. The near side mantle is between 70 and 100 degrees Celsius warmer than the far side. Not just on the surface, deep down, into the interior. The best explanation anyone has comes from the single largest impact crater in the known solar system, which happens to be on the far side of the moon. It's called the South Pole Aitken Basin, 2,500 kilometers wide, 8 kilometers deep, the impact that made it released energy roughly 1 trillion times greater than a nuclear bomb. And the theory is that the shockwave from that impact sent a thermal plume rolling through the moon's interior, a slow-motion wave of heat that swept all those radioactive elements to the near side, where they kept the magma warm and active for billions of years while the far side went cold and quiet. That's the theory. It's well supported. But here's the thing. Until June of 2024, every physical sample of moon rock that scientists had ever analyzed came from the near side. The Apollo missions, Chinese landers, Soviet probes, all near side. The far side was only ever studied from orbit, from radar, from spectrometers measuring reflected light. Then, China's Chang'e 6 mission landed inside that impact basin on the far side, scooped up rocks, and brought them home. The first far side samples in the history of spaceflight. A little under 2 kilograms of material that had never been touched. The results confirmed what the theory predicted. The far side mantle is drier, cooler, chemically different. The moon really does have two completely separate geological identities running all the way down. The Artemis 2 crew will be the first humans to look at the far side up close since 1972. They've been trained by geologists to recognize specific surface features. They'll take photographs. And some of what they photograph has never been seen by human eyes before. Number 8. The moon lied to us about its magnetic field for 50 years. We figured it out 5 weeks ago. The moon has no magnetic field today. It hasn't had one for about 900 million years. You already knew that. But here's what nobody told you. When Apollo astronauts brought rocks back from the moon, scientists discovered those rocks were magnetized. They had recorded a magnetic field, a strong one. Some samples showed fields comparable to or stronger than Earth's field today, which meant the moon, at some point in its past, had a magnetic dynamo running, a churning, molten core generating a global field like Earth's. The problem is that the moon's core is tiny, 1/7 the radius of the moon. Earth's core is about half its radius. The math didn't work. A core that small shouldn't be able to sustain a powerful magnetic field for the hundreds of millions of years the rocks seem to be recording. So scientists split into two camps. One side said the rocks proved a strong, sustained field, and the small core just had to be explained somehow. The other side said the small core proved the field must have been weak, and the rocks were misleading. Both sides had real evidence. Both sides were right. Neither side understood why. 5 weeks before the Artemis 2 launch, a team at Oxford figured it out over pints at a pub. One researcher was complaining about the problem. Her colleague asked a simple question: what if only certain rocks recorded a strong field because of what they were made of? They went back to the Apollo samples and measured titanium content. Every single sample that showed a strong magnetic field was high in titanium. Every sample that showed a weak field was low in titanium. Not a coincidence. The connection is physical. Titanium-rich rock at the moon's core mantle boundary melts at a lower temperature, and when it melts, it briefly pulls heat from the core in a way that drives the dynamo hard, a burst of strong magnetic field. Then the titanium rock rises as magma, erupts onto the surface, and cools. The dynamo goes quiet again. Each burst lasted somewhere between a few decades and 5,000 years. Then nothing. Then another burst, thousands of years later. The moon's magnetic field didn't hum along for 500 million years. It flickered. And here's the part that reframes everything. All 6 Apollo landings were on flat volcanic plains, exactly the terrain that's rich in titanium basalts. The missions accidentally sampled almost exclusively the rare moments when the field was anomalously strong, then concluded that was normal. 50 years of scientific debate built on a sampling bias nobody caught. The Artemis program lands at the South Pole in completely different terrain. The rocks there should tell a different story. We don't know what it is yet. Number 9, we don't actually know where the moon came from. The official answer is the giant impact hypothesis. 4.5 billion years ago, a Mars-sized planet called Theia collided with the early Earth. The impact was catastrophic, both bodies partially vaporized. Debris was flung into orbit. That debris clumped together and became the moon. It's a good theory. It explains the moon's size, its lack of iron, the angular momentum of the Earth-Moon system. It's almost certainly correct in broad strokes. Here's the problem. If Theia was a separate planet that formed somewhere else in the solar system, it should be chemically distinct from Earth. Every other body we've sampled, Mars, the asteroid belt, different meteorite classes, has its own isotopic fingerprint. The ratios of different oxygen isotopes, titanium isotopes, tungsten isotopes, these are like a geological accent that tells you where in the solar system something formed. The moon's accent is identical to Earth's. Not similar, identical. Across multiple independent measurement systems. The statistical odds of Theia coincidentally having the same isotopic fingerprint as the Earth are less than 1%, which means either Theia formed unusually close to Earth, or the collision was so violent that both bodies completely mixed and lost their individual identities, or something about our model is wrong. 3 different formation scenarios have been proposed to explain this, and none of them fully work. The most recent simulation suggests the moon might have formed in a matter of hours, not thousands of years, from a single violent event that put material directly into orbit before the debris could spread and differentiate. If that's right, everything about the moon's early chemistry has to be reconsidered. There's also this, and computer simulations published in 2023 suggest that 2 mysterious blobs sitting deep inside the Earth's mantle, continent-sized structures about 2,900 kilometers below your feet, might be pieces of Theia that never left. The planet that made the moon might still be inside the Earth right now, slowly being mixed into the mantle. We're flying people to an object we built using material from a planet we can't find, following an event we can't fully model, to study a surface we've only sampled from 1% of its area. Number 10. The crew is almost there. Monday, April 6th, the lunar flyby. At some point during the approach, the sun moves behind the moon from the crew's perspective. The lights go out. They'll be in the shadow of the moon, looking at the dark side, and NASA has given them a specific job during that window: watch for flashes. Look for the unexplained lights that have been recorded for 1,000 years and never explained. Watch for dust drifting up off the limb, the horizon glow that astronauts on Apollo 8 and 10 reported from orbit and that nobody has been close enough to study properly since. Look at the far side that nobody has photographed up close since 1972, the geologically silent hemisphere that we only got the first physical samples from 2 years ago. In a single flyby window, 4 people will be observing live evidence of at least 4 of the mysteries in this video simultaneously, and then they'll come home. They won't solve the radiation problem. There isn't a solution yet. They won't know what the long-term dust exposure does to a human body over a month on the surface, because nobody has spent a month on the surface. They won't know if the ice at the South Pole is mineable until someone drills into it, and the drill that was supposed to try tipped over before it could deploy. They won't know if the ground under the landing sites is seismically stable, because the last seismometer on the moon went dark in 1977, and nobody has put another one there. What they'll have is photographs, observations, data from sensors that are measuring their bodies being changed by an environment humans aren't built for. We are going back to the moon, partly because we don't understand it. And what the Artemis 2 crew is finding out right now, in real time, is that the closer you get, the stranger it gets.